All right, how's it going? I got your note. Your latest one sounded like you mostly had it figured out.
I hope so.
Okay, cool. All right, so ODP 213, lingering questions. So the goal is to take a string, add up the ASCII codes, right? Basically reduce mod 31 at the end, so running sum. There's different ways to go through a string. So here's one way. Right, so you can use a for loop that you can't see, an invisible for loop. There it is. For I equals 0, I less than string length of str I plus plus, right? And str bracket I lets you get to character I of the string. Yeah.
So when we are given that array, that's passing in like characters, right?
It's technically it's passing a memory address, which
Right,
is
but-
the location of the first character.
So within it, it would say something like hello.
Mhm.
But when we're setting the values equal to like an integer, like n, that's converting those into the ASCII codes to store the actual numbers.
Yeah, so when you say something like sum equals sum plus, right? It's taking that character. Well, a character is a byte. It's a short integer, and it's treating it as a 32-bit integer equal to that same value. So the character A has an ASCII code of 65. If I add that to an integer, I add 65 to the integer. So yeah, we can do a for loop. All right, we can do a for loop where instead of seeing if I is less than the string length, we can see if string bracket I is not the null terminator. Okay. This is totally legal, but it's a little unconventional, right? Usually this would probably go in a while loop more than a for loop. For loops, at least in my experience, you mostly see when you have an integer variable initialized to some value, compared to some value, and then incremented in some way. When you start putting in other conditions in here, like is this equal to that, and so on, while loop might be more conventional. This works perfectly fine, right? And I'm happy with either. But down the road, people might be more confused by that. I don't know. But that works fine. So would a while loop. Let me do this as a while loop. Right, so we increment I at the bottom, and the way we access this character is still str bracket I. But you can also do this with pointers. We can say something like this. So we can say, well, the thing that str is pointing to is not the null terminator. And then when we want to access the character that str is pointing to, we can say star str. Right, that's a character. And then at the bottom of our loop, we can actually say increment str. Because str is an address in memory. If we increment that, now str is pointing at the next character. Okay. The only thing to be aware of is you're changing the value of str. If it's just a local variable and you don't need the original value, that's totally fine. If you need the original value, save it somewhere or modify a copy. So this also works, right? And this is more pointery memory, right? This is more thinking of it as a pointer to a bunch of things in memory as opposed to a string, which is you know, what this is suggesting, right? It's just an array of characters. Yeah.
So are you like literally adding one, like to the address?
You're literally adding one to the address.
So would that work on something that's like not like the size of one, if that makes sense, like an integer?
Yeah, so here's my one thing that I don't really like much about C, which is if this is a pointer to an integer and I say plus plus pointer, it actually adds 4 to it, right? So that it points to the next integer, which makes sense and it's convenient, but it disturbs me a little bit. But yeah, so this pointer arithmetic is another way to work your way through an array. All right, so there's a for loop solution, right? Go through the buffer and add up each character. And I reduce mod 31 each time that I add just to keep the number small. Theoretically, if I had, you know, a billion characters in my string, my sum might blow up. If I keep reducing mod 31, my sum is never bigger than 30. So sometimes that's useful. But yeah, have a running sum, initialize it to 0, go through each character, add them up. Again, there's no special treatment with new lines in here, okay? The only thing that marks the end of a string is the null terminator /0, ASCII code 0, integer value 0. Okay, but we just do single quote /0. And if there happens to be a new line in buffer, just add its ASCII code and keep going. If there's a non-printable character in buffer, just add its ASCII code and keep going. Right? The only magic character is ASCII code 0, that's the null terminator. All right, so today's ODP, almost exactly the same function except your hash takes 2 arguments. It takes your character array and it takes a second argument, which we call a probe. And the only difference in behavior is you go through, you add up the ASCII codes of all the characters. At the very end, though, you also add the square of that second argument. So if I call hash and that second argument is a 0, it should give exactly the same thing as 213's hash gives. But if I call hash and that second argument is a 1, it should add 1 squared, which is 1, to the final value. And I'll get a number that's 1 bigger than what I got in ODP 213's hash. So hello, which used to give me a hash value of 4. If the second argument is a 1, it gives me a hash value of 5. If that second argument is a 2, you go ahead, you add up all the ASCII codes, you get 4, you add 2 squared, brings you up to 8. If that last argument is a 10, you'll add up all the ASCII codes, get a 4, you'll add 10 squared is 104, reduce that modulo 13, and you get 11. Right, 93 plus 11 gets you to 104. All right, and we don't need to know what this probe is all about, but we are going to talk about it at the end of class. But it's a different way to do hashing. It's a more complex hash function. It takes 2 arguments, the string you're hashing and then this integer that we call a probe. All right, so clear what to do for this one? All right, link it into the test bed, assess it. All right, so a couple of announcements. First of all, if you're making good progress on your SLP and you're on a good path with that, keep going. Okay, cover your ears. If you're at a point where you feel like you're thinking of changing gears on your SLP and it's kind of late because we're halfway through the middle of the second of 3/4, right? But if it's just not working for you, or you've done some research and cold fusion is harder than you thought it would be, or your partner got sucked up in a UFO and now you have to work alone, and they knew critical things right? So if you feel like I really think maybe I should switch projects, right? If you're interested in doing a project in Android app development, there's an opportunity that Izad has. He's looking for an Android app to basically interface with the electric car in the collaboratorium, to do some instrumentation. And it would basically be learning how to do Android development, making an app that would interface with some Arduino I/O to basically get sensor information and things like that. And it's a potentially pretty cool project to work on. If you've never done app development and you want to get into that, right, which is a bit of a learning curve, right? Downloading Android Studio and then figuring out all the stuff and writing code that's kind of Java-like, right, but that you can probably get by from knowing C, and we'll get to Java in a few weeks anyway. Talk to Izad if you want to know more details about what he's thinking of as far as a project, and then if you think that might be interesting, talk to me and we can figure out if it makes sense for you to change your SLP. Does that sound reasonable? All right, so that's an opportunity out there. Other announcement I wanted to make, there will be advisors from WSUV visiting this building on February 21st. So they'll be in the collaboratorium, there'll be a table set up in there. If you're transferring in fall and you have questions or concerns, or we're planning to talk to an advisor at WSU and haven't gotten to it or not, it's a good opportunity to get some one-on-one FaceTime and ask questions, voice concerns, things like that. There's a sign-up sheet on the window of the collaboratorium as you walk down the hall. It's on the right before you get to the door. There's a bunch of time slots listed there. There were still some openings a few hours ago when I walked by. So if you think you want to talk with an advisor while they're visiting, February 21st, go ahead and sign up for a time slot on that, and they'll be here. All right, I got all of PA2 graded. I haven't posted the grades and comments yet, but I got them graded this morning, and they look really good. Minor issues, memory leaks occasionally, and issues with deletion mostly, but by and large, it looks like people are on track as far as dereferencing pointers, accessing fields from a dereference pointer, using the arrow notation, doing mallocs, doing freeze, that kind of stuff. Looks like we're all pretty much in good shape. So I'm confident for you for PA3, right, which is putting together the list work from PA2 with what we're talking about this week, which is hashing. So I'll post the grades and comments later on today, and tomorrow we can go through some sample code and talk about specifics. But by and large, I got no concerns with most of what I saw, so you're in good shape. All right, so let's talk about PA3 some more. We started talking about the hash add function yesterday. We finished talking about hash add, and my punchline there was you don't need to do a lot of work. You're basically calling your list add function. Once you know which list to add your entry to, which you get by calling your hash function, you just pass that list to list add, pass the information you want to add, plate, first name, last name, and list add does all the work for you. Hash find is pretty much the same story. So you pass it a sentinel, a plate, a first name and a last name. Well, we need to know which linked list we want to search, and that's found by taking your license plate and running it through your hash function. The integer it gives you back, that element of your hash table, sorry, this is hash table. That element of your hash table is where you want it to search for the entry. So hash table is an array of hash entries. So you can do this in one line, right? Take your plate, run it through your hash function. That gives you an integer. Take that entry in your hash table. Okay, that's a character array. This is an integer. This is a hash entry. Bless you. All right, this is a hash entry, which is a pointer to a struct node. It's a sentinel node. Okay, our list find function expects a sentinel node followed by what it's looking for. So we can call list find, pass it your sentinel node, pass it the plate that you're looking for, pass it the first and last arguments, which will be populated with the first name and last name matching this plate if it's found in the list. So this will do a few things. It will search for the plate in this list. If it finds it, it will load the value of the first and last name into these two arguments, and it'll return a 1. If it doesn't find it, it'll return a 0, and these will be unchanged. Well, our goal for hash find is if we find this plate in the hash, change the value of these arguments first and last. That's those. Well, list find is going to do that. And we want hash find to return a 1 if it finds plate, return a 0 if it doesn't. So we can just return whatever list find gives us. Right? And hash find can be a one-line function. It's just wrapping around list find. Now, you don't have to do it in one line, right? Especially when you're developing it. If you want to put in debugs and print statements, right? Call your hash function, print out the index, make sure that's reasonable. Take that in your hash table, maybe call your list print function to see what that entry looks like, you know, and then pass plate first and last, print out what list find returned, print out the first and last, you know, and so on. But functionally, that's sufficient. All right, hash load should tell you how heavily loaded each cell is in the hash table. And if you implement the list functions that I ask you to, you have a list length function. It tells you how many nodes are in the linked list. So hash load, again, you don't have to really do a whole lot of work. For I equals 0 to hash table size minus 1, print out list length of hash table bracket I. Just go through your hash table. Each entry is a sentinel node. Pass each of those sentinels to list length one at a time and print out what it returns. Same thing with hash dump. Hash dump should show you the contents of a particular cell. Well, how do you do that? Well, if you take hash table bracket cell num, that's a linked list. Print out the contents of that list. How do we do that? Use list print. So this is another one-liner, if you like. List print parentheses, hash table bracket cell num. Okay, once you're rolling in this way, the sky's the limit. And we're going to go right into 223 in a few more weeks. And this is all we're going to be doing. Well, we're through some other stuff. when you're working in Java, like, you know, in industry, or you're doing the app development or something, you're just calling stuff that already exists. Right? Once in a while, you have to say I equals I plus 1. Mostly you just call stuff, you know, it's like cheating. There's very little real work that you have to do for most of what you're gonna write. It's when you get down to that kernel where you have to do something that hasn't been implemented yet that you have to sit down and actually like write the hard code, right? But you can have a lot of fun and get a lot of good output just by, you know, building wrappers around things that are already there for you. That's what most of app development is. You want to make a calculator app, right? It's like you don't have to figure out how to draw a button. You don't have to figure out how to display a number by lighting up pixels, you know. It's all just like bundled in there for you. You just have to put them together in the right way. It's like playing with Legos or something. If you wanted to make your own Lego block, that's a really hard thing to do. Well, we can do that too, because we're programmers. But you can get pretty far just taking pre-existing blocks and putting them together in creative ways. So this mindset is important to develop, right? I want to do my hash load, I'm just gonna call print. I want to do hash dump, I'm just gonna call that. And hash free is the same, right? To free my memory, I need to do two things. One, I need to free my hash table itself, but I also need to free all the memory associated with the lists in my hash table, right? Well, every entry in my hash table is a Sentinel node, and I have a list free function, which takes a Sentinel node and frees the list associated with that. So it's another for loop. For I equals 0 to hash size minus 1, list free, parentheses, hash table bracket I. I'll write that one out because it's a good representative. So that will free hash table 0, hash table 1, hash table through hash table 99 if we've got 100 things in our hash. And then when you're done, call the actual free function to free this array which you dynamically allocated in your hash init. All right, that's an array of hash entries. Just pass that to free. All right, so what about the list functions? So you've coded these to work with integers, right? You've got a list add, which adds a new node containing an integer to a list, and it actually adds it in sorted order, okay? I don't want you to add these license plates in sorted order. I just want you to add at the beginning of the list. So some of the code you wrote you don't actually need. We're never going to delete, so we don't need the delete code. Okay, we really just need the add and the search and the init and the free. So let's look at list init. So here's a list init. It should return a struct node star. And our goal is just to make a Sentinel node. So same as you've been doing, struct node star Sentinel. Well, we have to allocate space. So how much space do we need? Size of struct node. Right, and our struct node is more complex than it was. Alright, so it's a plate, a first, and a last, which are all car pointers, and then it's a pointer to the next node. So it's got 4 pieces to it. And then, since it's a sentinel and we have an empty list to begin with, set the next field equal to null. And then return the sentinel. So that's pretty much the same as PA2 init, right? The struct node is different, but that doesn't change our code. Now in PA2, a lot of times when we create a sentinel node, we like to give the data value of a particular field. So if we bump into it, we notice it, right? And we can do that here if we want. If we don't do that, we can leave the plate, first, and last fields alone. Okay, and I'm going to leave them alone for now because we're going to talk about how to add things to those next. So this works fine as an init. But if I try to do something with the Sentinel's plate field, for example, and I run this in Valgrind, I'll get a warning. It'll say I'm using an uninitialized location. But I'm going to assume we're never dealing with the data fields of the Sentinel node. The only thing we care about the Sentinel is what is it pointing to. If it's null, the list is empty. If it's not null, it's the first node of our list. Okay, so init is not bad. Let's look at add, because add is a good representative. So our list looks like this. Here's a sentinel. We've got 3 data fields and we've got a next. And this points to our first node, and that points to our second node, and so on. So that's our list. And we want to add a new license plate first name, last name node. All right, so let's see. Void list add. List add or add list? List add. So we got a sentinel, got a plate, first and last. Okay, make yourself a temporary. Malloc some space. Alright, enough space for a struct node. So that creates a new block, temp, 3 fields, and a next. Okay, we want to sandwich it into the beginning of our list, so we do the same thing we've done earlier. Take our new node's next field, set it equal to the sentinel's next field. That's going to take this field right here and make it point to that first node. And then sentinel next equals temp. That's going to change sentinel, so instead of pointing where it was, it points to temp. Bingo, we've inserted it into the beginning of the list. So temp's the first node of the list, it points to the old first node, points to the old second node, and so on. Okay, here's the slightly tricky part. Copy plate, first and last, into temp. Okay, this thing right here is a car star. That's a car star, that's a car star. This is next, which is a struct node star. Okay, these are character stars. We want to copy the license plate that we passed to our add function into this first field. So we could do something, so we can't use an equal sign. Okay, we need to use string copy. Our goal is to copy the characters from this argument into the characters pointed to by this field. Okay, if we just say temp arrow next, or temp arrow plate equals plate, that's just setting the addresses to be the same. That's saying that this points to wherever this points to. Well, this might be pointing to a temporary variable that's going to get reused in a few seconds. And when I change the value of that temporary variable, the value of this node suddenly changes. Okay, so we can't do that. Need to copy the characters themselves. So that's string copy. So we can say string copy temp arrow plate, comma plate. And that's a little loop that copies character for character up to and including the null terminator. Okay, so now it's just taking things from there, putting them wherever that's pointing. But that's going to segfault. Right, so here's a sample node, here's a main program, I malloc space for that, I set the next field to null, and I string copy this ABC123 into temp arrow plate. And if I run that, almost guaranteed segfault. So let's run it in GDB. I'm about to copy ABC123 into temp arrow plate. Well, temp is a location in memory, right? We got that from calling malloc. If I say show me what's at that location in memory, it's a struct node, and plate first, last, and next are all equal to 0. Okay, plate is supposed to be an address in memory, and the string copy is saying copy ABC123 to memory starting at this address, temp arrow plate. Well, that's a 0, and we can't write to memory location 0. And if I try to print what's at that location, temp arrow plate, it tells me I can't access memory location 0. That's your quintessential segfault. So we need to set up space with malloc. So before you can do the string copy, temp arrow plate equals malloc. Make room to copy plate. Okay, so big question, how much space do we need?
Size of plate.
Length of plate. Right, so we need as many bytes as we need to store the license plate. So how many bytes do we need to store ABC-123?
8.
Right, because
Null terminator.
you need a null terminator at the end. Okay, ABC-123 is 7 characters. If we do string length on that argument, we get a 7. But we also need a space for the null terminator, because when we copy 7 characters, we're actually copying 8 bytes. Right, there's this invisible null terminator that always gets carried along. So the amount that we want to malloc here is actually, string length of plate plus 1.
So the size of plate, that would just be as many bytes as a pointer number is.
Yeah, if plate is a char star, if it's declared as a char star and you do size of, you'll get back 8, no matter how many bytes it's pointing to.
Which conveniently works.
Which conveniently works until plate is bigger than 8 characters.
Yeah.
And if it's a lot bigger, it will put down a little time bomb for you. Right? So this is where I said before, never use size of on a variable. right? Because it's just too easy to accidentally pick up the size of an address instead of the size of a string. Now, if you actually declared plate to be a character bracket 500 and you do size of, it gives you 500, right? And in that case, it works perfectly fine. But so it's that possibility of doing what you think it's going to do or not that keeps me away from size of variables. Okay, this plus one is really, really critical, right? If I don't do a +1, guess what? My code's still going to work most of the time because malloc will always get me at least 32 bytes on this system. And if I want 8 bytes and I just say string length plate and I ask for 7 bytes, I still get 32 bytes, right? I got some wiggle room in there. And so chances are if I don't have that +1, my code's going to work great most of the time. Here's what happens though at 3 a.m. when you're done with 600 lines of code and you're ready to turn it in, you're doing your final tests, and you happen to have a license plate that's exactly 32 characters long, and you call malloc with 32 instead of 33, malloc gives you 32 bytes. And you need a 33rd byte for the null terminator, and you didn't malloc it, and now you're stepping on something else in memory. And a few minutes later in your program, you get a seg fault. And it's from something you did earlier that you already tested and was working fine, right? Those are the ones that are really hard to find. And you can use valgrind, right? And that will sometimes tell you when you step on something, right? So that's just one you kind of have to know and hope that you don't forget, or hope that you don't get a 32 character license plate or name.
Can you start accidentally accessing memory from other programs or operating
Yeah,
systems?
yeah. I mean, you won't mess up a program that's currently running somewhere else because everybody has their own virtual memory, but you can step on a location of memory that somebody else had used and pick up something from them. Or, in your program, you might have a flag that's set to non-zero when you want to exit, and you go ahead and write some character into that, and suddenly your loop exits for no apparent reason. All kinds of weird stuff is possible.
So you're saying that malloc would only get 32 bytes in this case right here?
If my plate was 32 characters, and I just said string length of plate,
Oh,
I would be asking for 32, it would give me 32.
okay.
And if I really wanted 33, I don't have enough. If my plate is 30 characters, and I do this and I ask for 30, I really wanted 31, well, I'm going to get 32 anyway. So I'll still have some extra stuff in there, right? But if you happen to ask for the amount that it's willing to give you exactly and it's not enough, then it'll show up as a problem. If my plate's 33 and I ask for 33, it'll give me 48. And so I've got a bunch of extra space in there. Just one of those things about C in particular, or assembly language. All right, so takeaway from this is basically when we're going to load values into the plate first and last fields of a node, we need to allocate space for them first.
And then when would you free that?
And then you free that when you delete that node, right? When you're freeing the entire list instead of just freeing, previous. First you have to free previous arrow plate, previous arrow first, previous arrow next, and then you can free previous as well. So it's 3 extra frees in your list free function. Don't just free a node, free the things that those fields point to first. And if you didn't do this for the sentinel, if you didn't set up these to point to anything, don't free the sentinel arrow plate, sentinel arrow first, because you'll seg fault. All right, so you gotta have some housekeeping on a nice clean sheet of paper or comments. I did get one awesome set of comments in PA2. I will definitely show it to future classes.
But not.
I can show it to this one. I'll find out if it's okay. Yeah, I'm still going to say you can't go wrong with too many comments. Throwing down the gauntlet. War and peace. All right, so So list add, basically the same as your add function for PA2, except always add at the beginning, right? So don't bother searching through. And when you copy your data into the node, malloc space for them, okay, for those 3 strings. Other than that, it's the same as you've already done. List find is a little bit easier, actually. So list find returns an int. So it takes a sentinel and then some strings. This is plate. First and last. And start off with a temporary, which is your first node of the list, or maybe null. So this is the traversal that you probably coded a bunch of times for your print, for your search, for your delete, and so on and so forth. So make a struct node pointer, set it equal to the thing the sentinel points to. So it's either pointing to the first node of the list or it's pointing to null if the list is empty. And so you can iterate, well, that node is not null. And what do we want to do? We want to know if the license plate in that node matches the argument plate. So plate's the thing that we're searching for. Okay, we've got 3 strings coming into this. Plate, first name, and last name, but we're searching just for the plate. Okay, if we find the plate in our list, then we want to take the first name and last name in the node and copy them to these 2 arguments, first name and last name. But plate's the key we're searching for. So how do we search for strings? We have to use string compare. So string compare the plate that we're searching for, and this node's plate is 0. Then we found the license plate. Okay, and again, we can't just say first equals temp arrow first. We have to use string copy. But in this case, we don't need to do any mallocs. The assumption is whoever called you passed an argument first, which is an array that's big enough to hold the first name. Okay, this is a dangerous assumption. Because if my first name happened to be 10 billion characters long, and somebody passes me a character array for first, which holds 32 bytes, I'm just going to step on whatever comes after that 32 bytes until I've copied all, gazillion characters from my first field. Right, so if you look at string copy, it'll warn you, beware of buffer overruns. See bugs. I never looked at the bug section. Right? If the destination string is not large enough, then anything might happen. I could win the lottery. Maybe we should do this. Okay? So here's an assumption you can make for PA3. Okay, and you got to be really careful not to misuse this assumption, so it's not written down. You can assume that the license plate, first name, last name that I give you in the database file will not exceed 32 characters each. Which means in your main program, when you call something like list find, you can pass a pointer to an array that holds 32 characters, and that will be safe. Okay. But you cannot assume, I don't want you to use that in defining what a struct node is. I don't want you to say plate is a 32 character array, first is a 32 character array. I want you to define those as char stars and then dynamically allocate space for them, like we were just talking about a few minutes ago.
To not assume that they would be 32 characters, wouldn't we just check to see if it is in this function? And then, if
There's no way to know how big it is. Well, I mean, you could check the string length of it, yes. The problem's not in this function, the problem is in your main program. So your hash function, in this case, is gonna call list find and say, you know, find me a license plate ABC123. Here's a variable I want you to load the first name into. Well, how big is that variable that's being passed to list find? Right, it's gotta have some fixed size.
Could you make it so that you use string copy, but you can write your own string copy that won't overwrite whatever's in that one?
Yeah, if you pass the length of first and last, you could do that, but you have to tell it how much space it has to work with, right? So you can do that, but it gets complicated, right? You either have to start passing lengths or ask it how big first and last are and then dynamically allocate memory and then say go ahead and load that in, or have it dynamically create first and last for you and pass them back to you or things like that. So you can assume the database file first, last, and plate fields will never be more than 32 characters. Okay, go ahead and run with that. But that's just to make it so that when you call something like list find, you don't have to worry about what if the first name is huge, right? You can just declare these to be 32 or 33. But
Is there any way to return more than one value from C?
not as the well, yeah, you can return a structure, and then you could have as many as you want. All right, but for these, right, dynamically allocate, what we've been talking about. Okay, so what do we do with list find, right? Go through, if you find that the plate matches, copy the first, copy the last, return 1. All right, otherwise, move down the list, go back up, iterate on your while loop. If you come out of the while loop, you did not find a place where the plate matched, just return a 0, and you're done. So pretty much the same thing as your search function for PA2, except you're using string compare, and instead of saying, well, we weren't searching for data, we were just seeing if this was in here, so we have to actually populate the first and last fields using string copy. All right, list length, just like print, but instead of printing, increment a counter, initialize it to 0. When you get to the end of the list, return the counter. That tells you how many nodes you have. List print is the same as print was, except you have to print out in this particular format. Instead of an integer, you want to print out something like plate colon, angle bracket, license plate, name colon, last name, comma, first name. Okay, so that's just formatting your printf statement differently with 3% s's. And make sure it's that format. And then list free is exactly the same, except as I said before, you free a node, free node arrow first, node arrow last, node arrow plate, and then free node. That's pretty much all I got for PA3. So work on it. Bring questions, and tomorrow I will go through some sample code for PA2, and then we'll talk a little more about hashes with probing, which is related to the ODP, and then we'll move over to a new data structure, stacks and queues. Yeah?
Can you suggest an order as far as, I mean, would you like to do all the list functions first?
Oh, okay. Yeah, I would tweak the list functions first, right? Because they're relatively minor changes, and that's also all of your work, right? Once you feel like these are working, then you just start putting wrappers around them. So then I would work on the hash functions. And I can give you an order for those if you want to. All right, cool. I will see you tomorrow then.